Everyone. So we just finished talking about how we can use Ohm's law for these simple circuits. And I said before that in those scenarios, Ohm's law is very basic, but it has a whole lot of potential that we can use it for and a lot of versatility. So we're going to actually take a step forward and start talking about some circuits that are a little bit more complex. Instead of dealing with one resistor, now we're going to deal with multiple resistors. Uh, but we have to be careful because when we add more resistors into a circuit, we can combine it in two different ways. So one of the ways that we can combine resistors in a circuit is in what's called a series circuit. Now, a series circuit is a single loop. It's a circuit that only contains one path. So if you start from the battery and you start following the paths that you can take, there's only one way that you can go, and you have to go through all those resistors. On the flip side, there's the other type is a parallel circuit. So in this connection, the resistors are actually connected on different branches and different loops, meaning that if you start at the battery and you start going towards one resistor, that path will take you back to the battery without going through the other two resistors. So essentially, when you go around, you can only pick one path at a time. So using these definitions, I want you to try and think about which of these four circuits is a simple circuit, which is a series, and which one's the parallel. So pause the video, work itself, and we'll go over in a second. All right, so the first one should be pretty simple. A simple circuit only has one resistor. The only one that has that is number one. Now, a series circuit, remember, was a single path going in one loop. Three is the only one that does that. I start at the battery, I go around, I go through each and every single resistor, and then I come back. There is no other path for me to take. Now, C is a little bit trickier. So, of the two remaining, which one's the parallel circuit? It turns out it's number two. Because, as I said before, you go through the battery, you cross one resistor, and you have to go back to the battery. You can't do one of these things because you can't go through a wire two times. So you can either go through the first resistor and then back to the battery, or through the second resistor and back to the battery. Um, Now, four is actually a complex circuit. We're not going to deal with this. The reason why this isn't considered a parallel circuit is because of the fact that when I go through the paths, even though these two are on different paths, I technically have to pass through these two resistors at the every single time. So this is actually a combination of a series and parallel circuit. Hence why it's called a complex circuit or sometimes called a combination circuit. All right, so the series circuit, there's a bunch of things that you need to know about these circuits because the way that they're set up gives it very unique properties. So for example, for a series circuit, the main thing to remember is that the current that goes through each of the resistors is the same. So if you have a circuit set up and you know that 2 amps passes through the first resistor, that means 2 amps of current goes through the second, the third, and the fourth. So, as I said before, a lot of times thinking of these circuits like hallways or water pipes or something like that ends up kind of making a little bit more sense. So, if we use the analogy of a hallway and the current being the students, we never have kids lost in the hallways because if a kid goes through one hallway, then if they're forced to travel in a straight line, then they have to go through the second and the third hallway. They wouldn't just magically disappear uh, between the hallways. Now, there's some other things that we need to talk about. So first off, there's this thing called equivalent resistance. Basically, what that means is if we take the resistor, uh, all of them connected in this way, we can actually combine them all into a single resistor that draws the same amount of current. So again, if these three resistors can draw a total of 2 amps from this battery, then I can set up a simple circuit with only one resistor that draws that same amount of current through the battery. And that resistance, that like the resistance to get it down to a simple circuit, is what we call the equivalent resistance. You could also think of it as the total resistance. So when resistors are connected in series, there's some things that are really nice to know off the bat, off the top of your head, about the total resistance. First is that it's always bigger than the biggest. So the total resistance, if this is 2, then the total resistance would have to be a number bigger than 2. Uh, every time we add a new resistor, it ends up increasing the total resistance. So the main thing about this, if we try to think about that, imagine these were traffic lights. So again, using as many different analogies as you can, if these are traffic lights and the amount of time, the effort, the amount of traffic that can go through, the more traffic lights and stops you force people to go through, the longer it's going to take for people to pass through that stretch. And the longer one of those lights is, the longer it takes on the whole. So that's kind of an analogy that you can use in order to kind of remember this. Now, as I said before, you don't need to remember this idea of that the total is bigger than the biggest, or that it increases as you add more. You could always calculate it and figure it out that way, but it's a way to save a significant amount of time if you can remember this. Now, parallel circuits are different. It's a little bit trickier with the analogy. So the analogy I say here is you could think of it as like going to the mall or going to cash registers. So when you go to a store, you can choose which cash register you go to. It doesn't matter which register you go to, though. You're still going to be paying the same amount of money, but you can choose which one to take. So you end up splitting up as a group between all the different registers. This actually makes it so that instead of forcing everyone to go through one resistor at a time, you can get a lot more people through the register, through the buying process, by having all these extra lanes, essentially, and registers. Uh, Now, if we think about the total resistance in the parallel case, then we end up finding that it's the exact opposite of the series. Instead of bigger than the biggest, it's now smaller than the smallest. So in total, the total resistance of this is going to be smaller than whatever our smallest resistor is. Again, that makes sense. If you have two registers open at a store, if one's really fast and the other one's really slow, it doesn't really matter because in total, you'll be able to get through more people through the store than if you just had that really fast person. And then decreasing the total resistance decreases every time you add a new resistor. Again, every time you add a new register, you're able to allow for more people to pass through the store in a given amount of time. So again, these are things that can really help with a lot of problems. Now, the best way that you handle these problems is you have to make a table. So you make a table, and it's called a VIR chart because it has VIR. You have to make sure that you put it in this order. If you don't put it in this order, then the tip that I'm about to show you will not work. You'll end up getting it wrong, and you'll have to figure it out on your own. The good thing, though, is that this follows Ohm's law, V equals IR. So you can actually use this to remember Ohm's law. And then what you do on the other side is you have whatever number of resistors you have, and then you have this total. Don't think that this total means sum. It's just, there's no better way that I could think of. So for the series and parallel circuit, the best way to deal with this is you're going to have to remember two phrases. For the series, you're going to have to remember the phrase SASA. So when you make your chart, right above it, you're going to write SASA. S-A-S-A. SASA stands for series circuit, add, same, add. What this means is that the numbers in this column should add up to the total. The numbers in this column are all going to be the same, and the numbers in this column should add up to the total. So if this is 1, 2, and 3, let's say, then these numbers should add up to the total resistance of 6. But this one, if this number is 2, the current through this resistor is 2, then they all have to be 2. These do not add to the total because, again, then it would be add. This is same. So every number should be the same. This allows for making you fill out the chart so quick and easy. It will take longer to make the chart than it will be to fill out the chart, and it will save a lot of time. For the parallel circuit, the phrase is PSAW. So PSAW. For parallel circuit, same, add, and weird. So in this one, the numbers in here are going to be weird. So you're not actually going to do anything in the column. You're going to figure this out using V equals IR. So again, we're going to fill this out. You can almost think of this as being like a Sudoku puzzle where you put the information that we know. We use this ideas of which columns add, which ones are the same, as well as V equals IR in order to fill out the rest of the table. All right. So first, we'll do this quick question. So pause video, work itself. We'll go in a second. All right, so they want to know which one has the smallest equivalent resistance. So this means that I should be looking for a parallel circuit. And then they want us to figure out the smallest. Well, parallel is always smaller than the smallest. So since this one has the smallest resistors in it, that one's going to be my smallest total resistance. If you actually, you don't really know how to do all of them yet, but the total resistance would be 4, 1, 0.5, and 2 respectively. So for the most part, you should be looking for the extremes, series with the biggest numbers, or parallel with the smallest. These are going to be your only two options in pretty much any of these types of questions. All right, here's the next question. Pause video, work itself, and we'll go over in a second. All right, so in here, they want us to fill out the total VIR chart. So again, we write our chart. We have two resistors. We write our phrase above it. Always start with the phrase SASA, since this is a series circuit. We put the battery in of 120 volts, and then we put the two resistors in. Now we use our phrase. I can't do anything with this column or this column, but I can add up these numbers to get 30 as my total resistance. I still can't do anything with the columns, so I look at the rows. I can use V equals IR, Ohm's law, divide 120 by 30, and I get 4. Well, now that I have this current, I know that the other two currents have to be the same because of SASA. And then once again, I can use I and R, multiply them to get the voltage, get 40 here and 80. And just as a double check, I just see, do these two numbers add to 120? They do, so that means I got it all right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this one's another series circuit. So again, we do the same thing. We write the phrase SASA. I put the voltage of 12 volts. I put my 4 resistors in here. Once again, I do pretty much the same thing where I add up the resistor columns to find that the total resistance is going to be 24. I'd use V equals IR again to find that the current through the entire circuit is 0.5, because the S in the column tells me that every other resistor has 0.5. Now that I have current and resistance, I can use V equals IR, Ohm's law, multiply them to get the voltage of 2 volts here, 3 for resistor 2, 4 for resistor 3, and then 3 for resistor 4. And just as a quick check, 2 plus 3 plus 4 plus 3 does equal 12, so my answers are correct. As you can see, there's really not much that I can do to make this type of question more difficult. All I can do is just add more resistors, but then as long as you can do the math very quickly in your head, like simple multiplication division, you should be able to fill this out very quickly. All right, so here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so now when I have my chart, instead of SASA, I'm going to use the other phrase, PSAW. Ignore the fact that this says series. I put in my voltage, and I put in my resistor values. Now, again, this is not a series circuit. This is not SASA. This column for resistor says weird. I can't add these because then I'd have an A there. Because it's weird, I don't do anything to this. Instead, I look at the voltage. This column should all be the same. So all these should be 12 volts. Now that I have this, I can use V equals IR, divide 12 by 6 to get the current, And then and then again, the currents add, so I'm not going to write 2 all the way down. I have to do v equals IR for each and every one to find their currents. So I get 2, 1, zero point 0.3, and 0.67 respectively. Now that I have all four, I can add them to get that the total current is 4. And then v equals IR, 12 divided by 4 gives us 3. Once again, as my check, is this weird? Yeah, that's pretty weird because these numbers wouldn't add to 3. But it makes sense to what I said before, that the total resistance will always be smaller than my smallest. 6 is my smallest resistance, so the total is smaller than that. So this is important to remember, that you actually pay attention to the phrase. You cannot believe how many times I have people make the chart, write the phrase above it, but then completely disregard it as they fill it out in whichever way they want. If you use SASA, make sure that you're actually filling out each column the way it's supposed to be. Columns that have S are all the same. Columns that have A get added. When you're doing parallel, you're using psaw and you're following the phrase above it. If you don't do it, there's no point in doing it. So uh, definitely make sure you're trying that out. All right, so here's next question. Pause the video, work itself, and we'll go over in a second. All right, so we have 2 resistors in a series circuit. So I'm going to write my phase SASA above it. The things I know, that it's 3 and 6. And then instead of the voltage, they tell me what the current is through the 4 ohm resistor. So kind of changing it up. But again, not much difference in that, because what I can do now is add up the resistors to get the total resistance to be 9. All the currents are the same, of 4. And then V equals IR, multiply the current and the resistance to get the voltage of 12 for R1, 24 for R2, and 36 for R3, or for the total. So from here, I could see that these numbers do add up to 36. Therefore, everything's kosher. That's pretty much it. We're just going to leave it at there. There's one more question, which we'll do in the next video. If you have any questions, let me know. You want to make sure that you practice using SASA and PSAW. They are a godsend. They are going to make filling out these charts significantly easier. All right. If you have any other questions, let me know. Join the extra help or message me on mine. With that said, good luck and have a great day.